I think we have to start. So we'll come to the last third part of our one non-associative day. So our next speaker is Tom de Medts, professor from Ghent University, and he is going to tell us about primitive axial algebras of Jordan type and three transposition groups. Welcome.
Yes, thank you. Thank you very much, Vladimir, for the introduction. I'm going to try to share my screen. I hope this will work smoothly. Okay, there we are. So I think you can see my screen if all goes well.
Yes, we do.
Yeah, perfect. Okay, so indeed, I will report on some recent work together with Louis Roman and Joab Segev, and it's in the part of a project of trying to understand primitive axial algebras of Jordan type. And in fact, it's also the same theme that you will see in the next. So the next talk is the one by Sergei Shpektorov. But we will be focusing on quite different things, but I think we some of the backgrounds is definitely common to my talk and Sergei's talk. Okay, so let's get started. So here is a bit of an overview. So first I will gently introduce you to axial algebras. I guess for many of you this is unknown territory, so you have probably not seen this before. So I will give definitions, examples, really try to do this kind of gradually. And the motivation of the current project comes from the theory of three transposition groups, which in itself has nothing to do with non-associative algebras. I think it's a nice kind of application to see how you can use non-associative algebras to do non-trivial things in other areas. And then the last part, I will go into some more detail and really talk about the strategy of what we did. Okay, so first the axial algebras part. So let's introduce these objects. And so the background or the setup is that we always have a commutative field. I assume that the characteristic is not equal to 2. And then A is a non-associative algebra, which is, of course, what we all like very much. So that's the general setup. It's going to be commutative. So we do have this assumption. So it's a commutative non-associative algebra. And a very important kind of type of elements that we will need are idempotents. So elements whose square is equal to the element itself. And we call these idempotent elements trivial if it's just 0 or 1. Maybe just a word about the element 1. My algebras are not assumed necessarily to be unital. So I do not always have an element that I call 1. But of course, if we have one, then 1 square is equal to 1. So that's something to point out here. And so you call it non-trivial if it's not equal to 0 and 1. And the important thing that we will be looking at are the multiplication operators. So they're denoted by ADI from a joint. So they're just left multiplication, right? So you just take this fixed element E in your algebra is idempotent, and you just consider left multiplication by this element. And what we do then is we look at the eigenspaces of this operator. So it's an operator from A to itself, so just viewed as a vector space, so it has eigenvalues, eigenspaces. And the corresponding eigenspace is going to be really important, and that's what we denote by this A lambda E. So remember that E is this idempotent that we chose, lambda is the eigenvalue. So it really means that we just take the elements with a property that if you multiply them by E, then you get lambda times the original elements. Yeah, so that's what we care about. And just by kind of to make the notation or the terminology a bit shorter, we call lambda an eigenvalue for the idempotent. If instead of saying that it's an eigenvalue for the left multiplication operator by the idempotent. Yeah. Right, so that's the starting point. Yeah, so I put it here on top again. So every now and then I have these little reminders that I put there to kind of, because, that's how it goes with computer presentation. If you click next, and the definitions are gone. So I think it's good to put them up every now and then. So we have this notion of an eigenvalue. And just as a kind of a very small remark and an observation, we do the following. So if you have an idempotent, then you always have these eigenvalues 0 and 1. So 1 is always an eigenvalue because E times E is equal to 1 times E. Yeah. And when A is unital, so when you have a unit, then 0 is also an eigenvalue because you have, let me maybe just write this down here. So you have E times 1 minus E is always equal to 0, of course. Yeah? So we have this fact that 1 minus E is always a 0 eigenvector. And now you observe as kind of a small exercise that if you have an associative algebra and unital, then in fact these are the only possible eigenvalues. Yeah, and in fact you get a nice decomposition of your algebra. It's very well known. You just have a decomposition here where you decompose your algebra into two parts. So A0E, A1E. So these are the only possibilities, and you get a nice direct sum decomposition. And importantly, you get a nice collection of what we call fusion laws. So let me at once put them in this table that I put below here. So if you take two elements that are in the zero eigenspace and you multiply them together, then again you get something in the zero eigenspace. Yeah, and similarly for the one eigenspace, you have two elements of the one eigenspace, and also their product lies in the one eigenspace. And then if you multiply something in the zero eigenspace and something in the one eigenspace, you get zero. Simply because, so this thing here is explained by the fact that E times 1 minus E is 0 again. Yeah, and this one is explained by the fact that E squared is equal to E. Yeah, and here the same for 1 minus E. 1 minus E is also an idempotent, so you also get this relation. And this explains this complete fusion rule because of associativity. Yeah, you can work this out as a small kind of toy example if you wish, and that's what you get. Yeah, so the resulting table here is actually quite nice to look at. It's quite elegant, and it contains a lot of information about it, about how these different spaces, these different subspaces actually multiply together. And that's what we call a fusion law. So the notion of fusion law is really important for us. And that's what we will take to the non-associative setting now, where it will become much more interesting. So I think that brings us more or less to the definition of an axial algebra. Yeah, indeed. So here we go. So it's first sight, maybe it looks a little bit technical in notation, but it's really a very nice concept, I think. So it's you start with what you call a fusion law. So this fusion law is something that you should think of as a table of the previous slide. Yeah? So this kind of small table containing information about how things multiply together. So it's nothing more than a map. So let me point this out here. Than a map, just from a set to the power set, to the power set of itself. So it takes pairs of elements to subsets of these elements, and it's a collection of eigenvalues in the cases that we care about. So this is why you have this important condition here that you maybe emphasize it a bit more, that your set is contained in the field. It's really a subset of the elements of the field. You have to think of it as eigenvalues. So we maybe also write that down here. You have to think eigenvalues. In fact, there is a somewhat more general way to do this, and I've just very briefly added a comment here at the bottom of the slide, so here, where we have put this in a more general context, which then gives rise to what we call axial decomposition algebras. It has several advantages, but it's not going to be relevant for this talk. So let's stick to the kind of simple and original definition from 2015 by Holregen and Spekterov, where we just have a fusion law, which really consists of eigenvalues. And then, just as in the associative example, we have a collection of subspaces, and for each subset, that's kind of a convenient notation here. For each subset, we will also write a lambda, so capital lambda E now for the direct sum of all these different subspaces that we have. And then we have the important notion of an axis. Yeah, so this gives rise to what we call an axis for the fusion law in our algebra. So this idempotent element will be an axis if you really get a nice decomposition of your algebra into the different eigenspaces for these different eigenvalues. So that's what I wrote down. Here. It is the important part. This very nice decomposition, which basically tells us that the left multiplication operator is diagonalizable. That's the meaning of this this expression. And then you have the nice facts, as again in the example on the previous slide, where the eigenspaces, the different eigenspaces multiply according to this nice fusion law. So that's what I wrote here. So this is the fact that they multiply nicely. And that's really what we refer to as the fusion law, which is then obeyed for this algebra. Yeah, so let me maybe just for a second go back to the previous slides, just to show you again what this was in this example. So again, the table that we had here at the bottom. So this table is really the fusion law. It's a very simple thing, consists of two values, 1 and 0, and they multiply according to this table. And then indeed, the fact that this fusion law holds for this algebra is expressed precisely by all these facts here. So the fact that all these different eigenspaces really multiply according to the given fusion. Okay. So don't hesitate to interrupt me, by the way. I cannot not see you, but don't hesitate to interrupt if you have any kind of questions, if I'm going too fast. Okay, so let me go back to this slide. So yeah, you have the definition of an axial algebra now, which really consists of these data. So here we have it, an axial algebra. It's really an algebra together with this collection of idempotent elements that give rise to these decompositions. And that's what we call an axial algebra. And there is one more small condition, which is this one here. So this condition tells us that we want to have sufficiently many of these axes. So we want to have a generating set of axes. So we want to have many idempotents in our algebra. Okay, and then we get the notion of an axial algebra. Right. This might look perhaps very general, very abstract, I don't know. So of course, I'm going to make this more concrete by giving you some more examples. So here we go. This is a very well-known class of examples. They also occurred in some of the earlier talks today, the Jordan algebras. So Jordan algebras are indeed commutative non-associative algebras, and they are defined by this simple rule that I wrote. So by this simple condition that a square b is a square ab. That's one of the possible ways to write down the definition of a Jordan algebra. It's maybe interesting to see in the context that we had that you can write this down in terms of these multiplication operators. It's really telling you that the multiplication by a and multiplication by a square are operators that commute with each other. Yeah, so it's really in this kind of operator context. There's also a way to do this in a different way using U operators for Jordan algebras. That also works in characteristic 2. It's a more characteristic 2 free way of doing that, introduced by McCrimmon. Well, but that's not super relevant for us today. And here is a very typical example of a Jordan algebra. You start from a non-commutative associative algebra now. That's a kind of the opposite situation of what we want to do. You take a non-commutative associative, a very, very nice classical algebra, and then you define this new product. Yeah, so you define a bullet b to be ab plus ba divided by 2. And that gives you a new algebra, which is, of course, now made commutative. So we've really done this in such a way that it's automatically commutative. But of course, you lose associativity. So this is a kind of a very nice and very well-known, very well-studied class of a non-commutative associative. Of commutative non-associative algebras, so the Jordan algebras. And they will play an important role also in the rest of my story. Maybe not directly, but it's kind of yeah, you will see. It's a class of examples that pops up. And these Jordan algebras, they are interesting from the point of view of idempotence and in the way that I just described, because indeed there is a very well-known and very important tool, which is called the Peirce decomposition. So if you have an idempotent, you have a non-trivial idempotent, then it's really a classical well-known fact that you can decompose your algebra into 3 pieces now. So you get 3 possible eigenvalues, namely you have 1, 0, but also 1/2 turning up now as an eigenvalue. And indeed, they multiply. So the decomposition of your algebra into these pieces multiplies nicely according to this very nice fusion law. Yeah, which really has lots of entries that are missing. And then the more entries that are missing, the more interesting it becomes, right? Because it means that it's very restricted. It means that you get a lot of restrictions on how these elements multiply together. And so for instance, I mean, to interpret it, just to give an example, something in the one eigenspace, something in the one half eigenspace, if you multiply these two together, it means that you automatically end up again in the one half eigenspace. Now you also see the interesting example here of this proper subset. It's not a singleton, it's like 1, 0. This means, if I write this down, this means that if you take something in the one half eigenspace, sorry, not, I'm writing this incorrectly, so J 1/2 with respect to my idempotent E, and again I take something in J 1/2 with respect to this idempotent, then what I get is something that ends up in the sum of the 0 and the 1 eigenspace. Yeah, that's a typical example of the situation where this kind of proper non-singleton subset arises. And that's the meaning of it. Okay, so this is really all very classical. It's contained, for instance, in Jacobson's Blue Book on Jordan algebras, just to give one example. Okay, and a really nice and interesting observation about this specific fusion law is that it has a grading. Yeah, it has a Z2 grading. It's Z2 graded. But what you can see nicely, so the fusion law itself breaks up into two pieces. And so it's like a plus part and a minus part, so to speak. So let's call this part the plus part. And this is the minus part. So also here we have the plus part and the minus part. And then indeed you see that two things in the plus part multiply again always to something in the plus part. And two things in the minus part, and so something here and something here also multiplies to something in the plus part again. And then minus times plus is minus and minus times plus is minus. Yeah, and that's what we call a Z2 grading of this fusion law. And this is really going to be crucial. And the fact that your fusion law has this grading really gives you a lot of interesting homomorphisms of the algebra. I will come to that in a minute. Okay, so these Jordan algebras are really nice from that point of view. Okay, a next example that's kind of the key motivating example for my talk today are the so-called Matsuo algebras. So these Matsuo algebras, they arise from three transposition groups. As I said, these will play an important kind of motivating role in my talk today. So let's have a closer look and first define these three transposition groups. It's a very easy group theoretic definition. So a three transposition group, so these things were studied deeply by Fisher. So it's a pair. It's a pair consisting of a group and a generating set for this group. So that's just what I wrote here. So a group for the generating set D. And importantly, D consists of involutions. That's a union of conjugacy classes of involutions. So subset of involutions invariant in their conjugation. And here comes the important requirement to make it into a three transposition groups. The order of any pair of the product of any pair of elements in D is always equal to 1, 2, or 3. Of course, it's only equal to 1 if D is equal to E. It's equal to 2 if D and E commute. And if the two elements do not commute, then you get a very small symmetric group of order 6. Yeah, so that's what's written here. So you get the order of the product is equal to 3. And yeah, I will come to examples also later in the three translation section when we come to this. But
Tom, there's a question in comments. What is an involution? Okay, maybe.
Okay. Yeah, an involution, thank you for asking. An involution is an element of order 2. So it's a non-trivial element with the property that the element multiplied with itself is equal to the identity. Okay, or put differently, the element is equal to its own inverse. Yeah, so these are really important elements in group theory. And once we have such a three transformation group, you can, in a kind of a very straightforward way, define a non-associative algebra, which is what we do here. So we have our given three transposition group. We have a parameter that we choose, which is called eta. So let me emphasize this here. So there is just a choice. You have a complete choice of a parameter eta, and then you define an algebra by taking as a basis precisely the set of these generating elements. Yes, so it's a basis as basis D. So the dimension of this algebra will be precisely the size of my set D. So let me maybe write that down too. So the dimension of my algebra is precisely the size of D. Okay. And it's defined by very simple relations, namely, first of all, the product of an element with itself is equal to itself. So in other words, these elements are involutions by definition. Are idempotent, I mean, by definition. If D and E commutes in the group, then I declare the product to be equal to 0. And then finally, the most interesting case is if the product has order 3, then I have a more complicated relation. Then I declare DE to be equal to this expression. Yeah, so eta over 2, D plus E, and then maybe I should also point out here that this D to the E, this is conjugation. Yeah, so D to the E is conjugation. In other words, is defined as E inverse DE, but of course these things are involution, so it's ED. Yeah, which is the same, by the way, as DED. Yeah, precisely because the order of DE is equal to 3. Okay, so that's this third element that occurs. It's again an element of capital D, precisely because it's invariant in the conjugation, this with capital D. And so you can write this down. You can write D plus E minus D conjugated by E, and that's my product of D. Okay, and of course, I mean, if you've never seen this before, then you think, okay, why this definition and why nothing else? And of course, the answer is because this one really behaves well. I mean, there is a really deeper motivation. It comes from vertex operator algebras, but I will not talk about the actual context of how it arose. But in any case, this turned out to be a really, really interesting way to define an algebraic structure. Okay. And in fact, one important reason is this one, precisely the fact that, again, these Matsuo algebras, they also satisfy exactly the same kind of fusion law as the one that we had before for Jordan algebras. Yeah, of course, for Jordan algebras, this value eta here was equal to 1/2. Now it's an arbitrary value, eta. It could be 1/2, could be something else. But other than that, the picture is exactly the same as for Jordan algebra. So that's really kind of a cool observation. Yeah. And this really makes these Matsuo algebras into axial algebras. Yeah, so really get very nice decompositions that multiply according to these rules. Yeah, kind of as a starting mark, you could of course now wonder, like, okay, well, are there examples of Jordan algebras? Are there also Matsuo algebras and Matsuo algebras or Jordan algebras? And indeed, we have studied this before. I have some earlier work with Felix Reren where we studied this in detail, but that's not going to be so relevant for today. So, but okay, it's a sensible question. And there is a little bit more. It's a bit going to be too relevant here, but yeah, the fact that these axial algebras are what we call primitive axial algebras. Yeah, and this primitivity means that the one eigenspace for the idempotent, right? So the elements with the property that A times E, so maybe to write this down again. So this M1E was precisely the collection of elements of the algebra such that EA is equal to 1 times itself, so equal to A. Yeah, that the only elements that satisfy this are multiples of E itself. Yeah, that's primitivity. It's equal to just the one-dimensional eigenspace span. Okay, and these Matsuo algebras, they satisfy this. Yeah, always. And these primitive axial algebras with this given fusion law, they will be the main focus of my talk today. It's an interesting and well-studied class of algebras. Also, Sergei Spektrov's talk will also, if I understand correctly, will also exclusively be dealing with this type of algebras. Okay, but I cannot resist mentioning this motivating and very important example. It's the Grice algebra, and this really is the origin of the whole area. I would say it's a huge algebra of dimension 196,884, originally defined by Bob Grice over the reals. And I mean, the reason for the whole existence and the invention of this algebra is its relation to the monster sporadic group. You know, it's the largest sporadic finite simple group of order of magnitude is like 10 to the 58, if I'm not mistaken. So it's an enormous group, and it was for a long time a huge mystery of why this group existed. And in some sense, this algebra explains its existence. And it has a beautiful fusion law with now it's more complicated. It has more values. It also includes these values 1/4, 1/4, 1/32 that pop up, and it's a more complicated fusion loop. But again, it's C2 graded, so it has this very nice grading. And yeah, so a beautiful story in itself. But I will not touch it at all in my talk. It's just as another motivating example. Okay, so then we come to the next part, which is the free transposition groups. So let's go into some more detail. Let me recall you the definition. Okay? The definition is that it's a group generated by a union of conjugacy classes of involutions and a product of any two elements as order at most 3. And here are some examples. And one of the easiest examples to understand is the full symmetric group on finite sets. Yeah, so let's say on elements. And for D, you take the collection of all transpositions in the symmetric group. So all elements that just like flip 2 elements. Yeah, so in fact, I've made a little picture here. So let me try to add some details to this picture. This is the picture for Sim4. Yeah, so Sim4, the symmetric group on 4 elements. What are the transpositions? They are 1, 2, 1, 3, and you will see that I write them in a peculiar way on this, in a very specific way on this little picture, as follows: 2, 4, and then here I have 1, 4. So what have I drawn? I've drawn what's called the Fisher space. Yeah, so let me just write down this word, Fisher space. It's kind of a geometric picture where I draw the elements of D. Yeah, so these 6 elements that I've drawn here, these are the 6 elements of D. So in this case, let me maybe also add that D contains 6 elements. Yeah. And the lines that I've drawn are precisely like the elements that are not commuting with each other. So that really have the property that the product of 2 elements has order 3. And then again, you get a third involution, which is precisely like the first conjugated by the second, as I explained previously. And they form lines. They form lines in this Fisher space. So for instance, you have this example here. So if I have 1, 2 and 1, 3, if I conjugate 1, 2 by 1, 3, I get precisely 2, 3. Yeah, and also it also works in the other direction. If I take 2, 3 and I conjugate by 1, 3, I get 1, 2, and so on. And 1, 2, and 3, 4 are not connected. They commute, right? 1, 2, and 3, 4 are 2 disjoint flips, so they do not commute, and they are not connected by them. And this picture basically contains all the information you need to construct the algebra, right? And that's kind of also an interesting way to think about these things. You can go from the picture, from the Fisher space, directly to the algebraic structure, to the Matsuo algebra. Yeah. And the second example, so that's the picture on the right, is already a bit more complicated. That's the picture that you get from taking the group that I denoted here by 3 square column 2. It's a very kind of a typical finite group theory notation. It's a shorthand for this thing, right? So I take 2 copies of C3, so I take an elementary Abelian group of order 9, and then I act on it by inversion, and I take the semi-direct products of these 2. And then I get a group of order 18. Yeah? So this group has order 18. So let me also write that down here. So the group has order 18. And D consists in this case of 9 elements. And all the elements that are not in the original C3 cross C3, they are all involutions. And that's what you get. And that's the picture on the right. It's a very well-known picture also. This is the so-called affine plane of order 3. Okay. Right. And these are the kind of the 2 smallest interesting examples that you can. There are some more examples, but I will just list them briefly. I mean, there are more than those, but this is like to show it that there are non-trivial things going on, and you really get interesting examples popping up. You get orthogonal groups. Orthogonal groups over the field with 2 elements. So maybe let me emphasize this fact that typically you get things over the field with 2 elements. Yeah? Orthogonal groups, symplectic groups, unitary groups. Yeah, in each case, for D, you take then transactions in these groups. In a similar way, and maybe it's somewhat more surprising, you also get examples over the field with 3 elements. Yeah? And then, of course, you have to be more clever in how you can get involution, but you can get them by taking certain reflections. Reflections, which is a well-defined notion if you have an orthogonal group, and you do that, you take a very specific conjugacy class of reflections, and in this case, you get a very specific kind of orthogonal group, and this one is also a 3 transposition group. So that's an infinite class of examples, right? But then interestingly, you get these things on the last slide, the Fisher groups. Right? So these are 3 of the the very interesting and quite large sporadic finite simple groups. So we've uncovered the monster already. Here are 3 more of those groups, of those only 26 sporadic groups. And in fact, it is also how Fisher discovered them. He was studying 3 transformation groups because he was trying to understand their structure, trying to give a classification. And that's how he encountered and discovered the Fisher groups. So they're really, really very beautiful finite simple groups. Okay.
And what is the dimension in the last case? It's comparable with the size of these groups, or?
It's substantial. It's I don't know exactly. It's if I'm not mistaken, the order of magnitude of some of these groups is like I have a number 3 to the 12, but it's smaller than that for Fisher.
Yeah, I mean
24.
The corresponding algebra will be.
That's right. So that's the size
algebra.
of B. That's the size of D. So they're huge.
Yes,
algebra.
right, but
exactly.
D.
Yeah, that's exactly that's the size of D. So it's like between the size of D, if I'm not mistaken, but I could be wrong. For one of these examples, the size of D is like 2 times 3 to the 12, or to the 11. So something around this. Yeah, huge. Yeah, really difficult to kind of write down explicitly in whatever form. Right. So here's a bit of a kind of classification type results. So first of all, it's kind of relevant, but to know that very often the theory is done like up to central type. And so that's kind of the first definition here. So this notion of central type. Basically, it kind of means that you can ignore central extensions and they give rise to the same Fisher space. And it's also, I mean, from our point of view, also you cannot see the difference. If 2 transformation groups have the same central type, then also the Matsu algebras will be exactly the same. Yeah, so that's a kind of a very natural kind of equivalence relation on class of 3 transformation groups. And yeah, here comes kind of the notion that will be really relevant for us is like the generation by a small number of elements. So in this case, we have the fact, the assumption that our group is generated by 3 elements from D, but not by less than 3, yeah, which is really tiny. I mean, these are really very small examples. And in this case, the central type, so the essential part of the group, is exactly one of these 2 examples that I've drawn, for which I've drawn the picture in the previous slide. So just like SIM4 or this group of over 18. And these are the only 2. And that's not hard to show. I mean, it's first appeared in a paper by Fisher in 71, but it's really elementary, I would say. Much less elementary is the next case of generation by 4 elements. Yeah, so if you go to generation by 4 elements from D, but not by less than 4, then suddenly you get 6 different types. Yeah, and as you can see, they become more substantial. Yeah, so you have symmetric group on 5 elements, of course, to be expected. Then kind of I would say kind of a variation of that is a wild group of type D4, yeah, which is also a cluster group, just like the symmetric group of over 5. And then you get some examples like the 3 cubed Sim4 is kind of a generalization of the higher dimensional version of the second example we had, like the 3 square column 2. The 4th example here, this one corresponds to affine space now, so affine 3 space, 3-dimensional space over the field with 3 elements. And then you get more complicated examples that are not so easy to define, like in a few minutes. Namely 2 to the 1 plus 6 extended by SU3 2 prime. And then a very nice example, I think, which is already a very, very large group, right? Of over 3 to the 10 times 2, which is Marshall-Hall's group, but which still has a very kind of modest generating set of consisting of 81 elements. Yeah, the size of D is 81. Okay. So these are the ones that we get. And okay, I mean, proving this is already like non-trivial, really requires quite a bit of work and serious group theory, right? Okay. And let me maybe here, go into just for fun. I mean, I'm not going to really need this, but just for fun, let's look in detail what the axial algebra, so the Matsuo algebra, corresponding to this largest example, what it looks like. And it's kind of interesting that you can write it down explicitly very, very easily. I mean, I found this in a paper by Lacaze and Beneteau from '83, which kind of it's not a well-known paper. It was a bit hidden in the literature, but here is a very simple, explicit description of this quite complicated, otherwise quite complicated group, right? So that is how you get the Matsuo algebra. It's not maybe not even super necessary to go in full detail in the construction, but you start from the vector space, four-dimensional space over F3, which has exactly the right number of elements, so this 81. Yeah? And then you kind of magically define an operation bullet, which is defined on the first three components in the natural way, so just like pairwise addition. But then on the fourth component, you kind of add a strange error term. It is the strange kind of new term that you correct, that you use to correct it. And then you define this kind of funny multiplication, d star e, which is d bullet e bullet d bullet e in this order. And that you use now as inputs in your multiplication, which of course you recognize. This thing is like the Matsuo type multiplication that you use as an input. And out comes the Matsuo algebra corresponding to whole street transposition. Yeah, so I think it's a really simple, explicit construction. And in fact, I mean, of course, as you can guess, this is extremely easy also to implement on a computer. And in fact, I did it at some point, so I implemented this, and I used this a lot to experiment. I mean, it's a really beautiful example. It's non-trivial, and you can ask for identities and try to check whether certain identities hold and so on. And so it has been very useful. Okay. And here is a nice kind of result that relates to the full classification of free transposition groups, which was done by work of Van Scherpes and John Hall in around '95. And in particular, they show that if you have a three transposition group which is generated by a finite number of elements, so like we had 3 and 4 in the previous case, if you keep this number finite, then in particular the whole group is finite. And you might think this is obvious, but it's not obvious at all. And the only proof which is known is using the full classification. That you really have to go through the whole story, through the whole classification to get this result. Yeah? And in fact, so Scherpes and Hall, they kind of indicate that it would be useful, or at least kind of valuable, to have a better understanding of why this is true. And in fact, our strategy or our approach or idea is exactly to try to use non-associative algebras to give a different proof of this rule. And we have not succeeded yet in the full generality. I mean, it's a challenging problem, but we have made some interesting progress, I think. So just to remind you, here is the definition again of a primitive axial algebra of Jordan type eta. So this is precisely, as you can see, one which has this given fusion law, right, with all the conditions that we had before. And you can rephrase this question as follows. So this is the original question of Scherpes-Hall. Here is the question double star. So you take a primitive axial algebra of Jordan type, assume that it's generated by a finite set of axes, so of idempotents. Does it follow then that A is finite dimensional? That's the question. All right. And if this is true, then in particular we have a new proof of the statement. Yeah, this is just what you get by plugging in a three transition group, get the corresponding Matsuo algebra. This is the primitive axial algebra of Jordan by eta, and you would have the result. And in fact, you can even show that it's equivalent for eta different from 1/2. You have an equivalence between these two. But in any case, we do it for general eta, and it's a more general result than just this result. Okay, so that's our strategy.
But at this point, so of course there are no direction backwards from this multiplication table towards combinatorial picture, right? So you have only one direction.
Yeah, no. So the reason that for eta different from 1/2 you do get both directions has to do with the fact that for eta different from 1/2, it's known that all the axial algebras, primitive axial algebras of Jordan type eta, are Matsuo algebras or quotient of Matsuo algebras, so they arise from from three association groups. So that's why I wrote that it's an equivalence in this case. Yeah. Right, so here's our question again. So let me focus on what's known so far. So the important things here are, first of all, the result of Gorshkov and Starolatov from a couple of years ago, where they have a paper dealing specifically with three generated primitive axial algebras, and they go in substantial detail. They do lots of computations. They really try to give a complete classification, and in particular, they get that the dimension of such an algebra is at most 9. And that is bound to shock. So you really get 9-dimensional examples, which we've seen before. We had these Fisher spaces with 9 points for the affine planes. So they really give examples of 9-dimensional, three-generated primitive axial algebras of Jordan type. And here is our result that I want to discuss a bit, which is the fact that for 4 generated, we get this upper bound of 81. And again, this bound is sharp. We just seen the example. I've just shown you this very explicit example of this 81-dimensional algebra, which is an example of a 4-generated primitive axial algebra of Jordan. And then indeed, so the next case I was trying to hint at a bit is this going to be really substantially more difficult. The conjectural upper bound is 3 to the 12 in this case. And also these Fisher groups arise. They are a little bit smaller than that in terms of the in terms of the size of the so the dimension of the algebra, but it's kind of the same order of magnitude. So that's going to be really substantially more difficult again. Okay, so that brings me to the last part. So let me see to what extent I can go in some detail here. So here's what we do. So we start, to begin with, we start with any axial algebra with a Z2 graded fusion law. And a very important consequence of having such a Z2 grading is the fact that you have many involutions in the automorphism of the algebra. So these are the things that what we call the Miyamoto involutions. Yeah. And they are very simply defined by fixing elements in the plus part of your grading. So this pi plus here is the plus part. This pi minus is this minus part occurring here. So you fix everything in the plus part of the grading, and you negate everything in the minus part of the grading. And because of the fact that your fusion law is Z2 graded, this will define an automorphism of the algebra, right? Because plus times plus is plus, minus times minus is plus, and so on. So these things are match up well and really define an automorphism. But that's kind of the crucial thing here, right? So that you get automorphism of your algebra. Okay. And so if you collect all of them for all possible axes, then you get a very nice, very large group of automorphisms. It's a subgroup of the automorphism of the algebra, the Miyamoto group. I'm not going to say too much about this, but the important tool for us is the following, which yeah, as you will see, it will play a crucial role in what follows, and it's the notion of what we call a Miyamoto sequence. Yeah, and it's nothing more than just a product of Miyamoto involutions. Yeah, so it's extremely simple to define, but we introduce a special notation for this. So this is here. It's kind of a very yeah, nicely looking kind of a double square bracket notation. Just means that you take the product of a corresponding Miyamoto involution. Yeah, so this is again an automorphism of the algebra. Okay, so these are the things that we consider. What do we do with that? So yeah, I've repeated the definition here as a reminder. We collect we kind of make larger and larger subsets of our algebra. So we start with just what I've written here. So you just start with S0, which is just the a generating set of axes. So this is like in a situation that just contains 4 elements. Yeah, the set S, and we just take the subspace of the algebra spanned by these 4 elements. And then we make larger and larger sets by applying longer and longer Miyamoto sequences, so by applying more and more of these Miyamoto involutions to it. And that's what we denote by this S, I. Yeah, so it means that we apply Miyamoto sequences here, Miyamoto sequences of length at most I. Yeah, so you get kind of a filtration. Yeah, you get a very nice filtration of your algebra into larger and larger pieces. And then the important observations for our results. So remember that we want to show finite dimensionality. And the important observation is that if at some point this filtration becomes stable, so if Sn is equal to Sn plus 1 at some point, then you're done. Then you know that you have the whole algebra. Okay? Then A is equal to Sn. Okay? And that's the kind of a trick. I mean, that's the way that you can really use these sequences to get something controlled and to know when your game is over, so to speak. And here is a kind of a really important way to get a handle on this, because if you start computing just Miyamoto sequences or products in your algebra, if you wish, then very quickly you kind of get lost. I mean, you lose control of what's happening. The expressions are just too wild. I mean, just look at the paper of Khoshkov and Stavrotev, and what they did already in the tree-generated case, and it's full of very complicated expressions, and you get lost. So here is the trick to actually handle this, to actually get control over what's happening. And this is the trick. We define what we call I equivalence, so an I equivalence relation, by declaring that the elements are equal modulo elements in Si. So modulo elements in this kind of ith level of this filtration, right? So you can kind of think of this filtration as something like this, right? And you kind of have larger and larger parts of your algebra, and you're trying to ignore what's below a certain level. Yeah, and you work modulo the level. That's kind of the key trick to get going. Yeah. And okay, you make a couple of very small observations first, namely that you can go from a certain level to a higher level. Yeah, but either by doing nothing or by applying a Miyamoto sequence, you keep control over what's happening in this kind of level structure here. And okay, another tool, and that's also a key observation, and I think it's a nice thing to remember. I mean, I'm sure this applies to many more algebras than just the one that we consider. The Miyamoto maps themselves are much better behaved than the multiplication. And you also see that in, for instance, people who know about Jordan algebras will also recognize this. In a Jordan algebra, you rarely work with the actual multiplication. You very quickly switch to the U operators, the V operators, and so on. And that's what you do, and that's how you work with these algebras. But the same is true here. The initial approach that we did was working with multiplication and like trying to get a hold on the generating sets. But you get lost. It's impossible. The complications are just too difficult and really ugly. And instead we use the Miyamoto maps. And here is the reason why this makes sense. I mean, this is this kind of small, this very small kind of identity here, which tells you that if you take one of these Miyamoto involutions, then in fact, what you see is that you have the multiplication occurring here. There is also something which is then called the Frobenius form, and let's maybe not go into too much detail here. But up to this kind of Frobenius form knowledge, knowing the multiplication or knowing the Miyamoto maps is equivalent. So you can indeed switch from one to the other without losing information. Yeah, and that's kind of the thing. So from now on, we really use these Miyamoto sequences. And okay, let me maybe see in terms of time. I think I will be skipping some of the details here, but I will make my slides available if you want to look at it in more detail. But here are some more details about how you can actually now get started. You can compute expressions like AB minus BA gives you a very simple expression which is shorter, right? This thing is on the 0 level. This is in the 1 level, so you get kind of equivalences. As you see here, AB and BA are like 0 equivalent. You also get very nice expressions like AA always vanishes, ABA is now AB, things like that. And you get going, and you prove things about expressions like ABA and BABA and so on. And that's how you get started. You make longer and longer of these Miyamoto sequences, and you try to simplify modulo lower levels in your picture. Yeah? And at this point, you still need the multiplication like once to really get kind of the bootstrap, let's say, to get started. But from now on, we never ever use the multiplication again. Yeah, so from this point, it's all Miyamoto sequences, and you try to do things with Miyamoto sequences. And Yeah, I will not have time to do these things in detail, but maybe to tell you the story here is that this is a very simple kind of level. I wanted to show this as an example, but yeah, I'll do it. But these are really simple things, and you see this is the complete proof of 1 and 2 already. So it's very, very short arguments, very short computations with these things. And yeah, so this is the proof of 3, also very short. And only using these things is already sufficient to recover the 3 generated case. Yeah, so the 3 generated case by Goshkov and Stavrolitov from 2020. And this is just how you do it. You just build this kind of you build these elements level by level. You start with level A, B, C, then you take a higher level, and you just see that you don't need anything else because AB was 0 equivalent to BA. So you don't need the other elements and so on. And then you just see what can happen if you apply again like A, B, and C to level 1, then you get exactly level 2. And if you start with level 2, then because of these expressions, you never get higher than level 2. You're done at level 2, and that's it. And that's the story, right? So you get the precise upper bound of 9 that they also discovered. And maybe I'm almost at the end here, but this is the more difficult version for 4 generators. And of course, I mean, the precise things are not so important for this talk. I mean, what I want to show is that the things get more and more complicated. Yes, so you get more and more longer expressions. So for instance, here you get suddenly, so this is where 4 elements occur, like A, B, A, C, D, the C, D, C, A, B, things like that. So you get a kind of strange kind of, we call them rewriting. It's really like a game with trying to rewrite these sequences in terms of other sequences. And it's really tricky sometimes to get the correct like equivalent. So for instance, proving this one, that so these are elements of S5, right? And proving that these two are 4 equivalent is easy. But in fact, you also made them like 3 equivalent. I mean, you still have to go like deeper down in that level, and that becomes like increasingly more difficult. Yeah. The last one is also like a story because the one here is the one that you need to close down, right? It's like saying that if you have something of length 6, you apply Miyamoto, you do not get longer than length 6. And that was really a tricky one. I mean, this one, initially I thought I had a complete proof of everything, but then I noticed there was a gap. This one was still missing. And then it took quite a while, but then Yoav, so the quarter Yoav Sega, he then came up with a complete proof and like, yeah, I found the proof. But it was 6 pages long. I mean, just proving the single thing was 6 pages long. It was like, oh wow, what is this? And then in the end, I mean, I looked at it that it was in fact a way to take a serious shortcut, and we managed to simplify it to less than 2 pages now, just this expression. So, but it's really yeah, very pleasant and really fun kind of game to play. Um, yeah, with additional tricks. I mean, it's really not all straightforward. You really need to be. Sometimes you have to rechoose your generating set in a clever way and so on. So it's okay. A lot of things going on in this in this thing that I just wrote on a single proposition. And this is the how it then ends. So this is then the kind of the equivalence of the previous slide, where it is for the 3 generated case. This is how you then do the 4 generated case. And again, you kind of gradually build up the different levels. And this time you really have to go up, like it's kind of the same picture, right, as before. You have this picture with different levels, and they become increasingly more difficult. So the 0 level is this one, and that would become a 0 with just these 4 elements. And then you go higher and higher. And then when you get to level 6, then yeah, you get to this point, and then because of the previous result, you cannot go higher up in level, and then you know that you've kind of wrapped up, right? You really there's no way to get more elements than the ones you already have, and you have very good control over what's happening in each level, and you can even write down like specifically what the bounds are in each level. And at the end, you get kind of magically get exactly the upper bound of 81, which is the one that we required. That we know is short because of the example that we have. Okay, that's all I wanted to say. Thank you.
Thank you, Tom, for a very interesting talk and many nice results. Okay, inspiration. Okay, so now we have time for questions, comments. Okay, welcome. Okay. Okay. Antonio,
there
okay.
is a question, I think.
Hi. Yeah. So when defining these axial algebras, how close you are from the three transposition group you start with? I mean, the group acts here by conjugation, right? Because
yeah, I can maybe try to go back to the relevant slide. Yeah, so this is the one where I defined schema 2 algebra.
yeah. So then, I mean, the group G acts on this algebra by just conjugation on the basis, right? Because
yes, exactly.
you stay inside of the same conjugacy class. But then
Yes,
how close you are with G? I mean, could be, I mean,
Oh.
in principle could be larger, right?
The
group of
holomorphism group
automorphism.
of the algebra can definitely be larger, that's true. But what is a very close connection is this Miyamoto group that I defined later. So the Miyamoto group is the one defined by these Miyamoto involutions, the group generated by this Miyamoto involution. And that group is essentially the transposition group itself. And by essentially, I mean, it's again, this kind of a subtlety about the fact that you can lose like the center of the group.
Okay, so the
So you can model
projected
some
version of the three transposition group has.
Yes,
say,
exactly. Yeah, that's
Okay.
the Miyamoto group. But indeed, the full automorphism group can be large. It can sometimes be infinite even. In the case that it happens to be coincide with a Jordan algebra, would typically be an infinite group. That can really happen. In fact, I think that Sergei's result will be Sergei's talk will be dealing, I think, to some extent with the question of if you have a finite automorphism group, that you have more information. But we will see.
And then the second question was these axial algebras, the group of automorphisms runs in every special class of groups. I mean, there will be, of course, algebraically defined groups, right? But
sorry,
they have something.
Again, the question is?
Oh, that. For instance, do you know if any group, any finite group of any algebraic group defined over case one of the automorphisms group, or could be represented at the automorphisms group of these algebras, axial algebras? Or?
Well, in general, that's I guess too much to hope for, especially if it depends on whether you impose fusion laws to begin with. In a certain sense, I mean, any algebra is an extra algebra for some fusion law, but it will of course be like a full stupid fusion law where you don't impose any kind of additional relations. But it becomes interesting if you fix a certain type of fusion law in advance to begin with.
Okay.
But indeed, you can get a lot of information out of the representation theory. So that's actually a very interesting question that you're asking. So if you take your favorite finite group or algebraic group and you look at its representation theory, then quite often you can see from representation theory, for instance, that if you have a representation with a property that the symmetric square contains a copy of the original representation, then it means that there exists a commutative algebra on that representation.
Okay.
Things like that. So there are really ways to construct algebras starting from a representation theory of the actual groups. And indeed, in many cases, they will actually be of axial.
And then a kind of stupid questions. I saw that when you get the trivial morphisms, you decide that the group of eigenvalues is the empty set. Is it just a convention or a way of, or maybe I got it wrong?
Sorry,
when you describe the fusion of to be used, it seems to me that whenever you get the trivial map, you define, like there, right?
Yeah.
You define the set of eigenvalues to be the empty set.
To be
the empty
no,
set.
so the meaning the meaning of this, for instance, of this empty set here is the fact that if you take something in this eigenspace and you multiply it by something in this eigenspace, and what you get is just always equal to 0.
Yeah. But that means that the zero is an eigenvalue. Then my question was whether that was a convention or something you want that to be defined to be empty somehow by some reason.
The convention is that the let me also see
the trivial map.
The convention is that sorry. Here the convention, it's probably this convention that you are referring.
Okay,
so if you have the empty set, then it means that it's just like the zero subspace.
Yeah, okay, great. Thank you.
Yeah, sure. Thank you.
Thank you again. We have not so much time. Okay, some several seconds. the next talk, but okay. So maybe my questions remained unanswered, but okay, many thanks again for a talk. We have to go further to the next speaker, right? Okay, thank you again.